Okay, so in this video we're going to go ahead and explore oscillation of a system with 1 degree of freedom. This will be actually a fairly short video, but I wasn't quite sure where to integrate it with the others. So let's go take a look at our system here. So let's say we're near equilibrium. Yeah, I can spell today. Which we'll decree to be where our generalized coordinate is 0. So we can expand our potential energy as a function of Q. So it'll be the potential evaluated at the equilibrium plus Q times the first derivative with respect to Q evaluated at equilibrium. So keep in mind I use a prime to mean that I'm differentiating with respect to the generalized coordinate. Dots are reserved for time derivatives. Plus 1/2 Q squared V double prime and so forth. Alright, now the first two terms are going to drop out. This one we're going to set to 0 because we're always free to just add or subtract a constant to make that happen. And here V prime at 0 has to equal 0. That's required for equilibrium. So I'm just left with the quadratic term being the first term that counts. And since we're near equilibrium, we don't have to worry about higher order terms. So we'll say it's 1/2 Q squared times the second derivative evaluated at equilibrium. All right. So we can write our kinetic energy as 1/2. And I'm going to write sort of like a half-sized capital M, Q dot squared. And we should view this as being a generalized mass. So it could be a mass, or it could be a moment of inertia. Or it could be something truly horrifying. All right, so then we can go ahead and write our Lagrangian, T minus V. So this will be 1/2 our generalized mass Q dot squared minus 1/2 Q squared times V naught double prime. Okay, so Lagrange's equations of motion, say partial L partial Q minus d dt of partial L partial Q dot equals 0. So differentiating this with respect to Q, bring down 2, cancel the half, I'm left with minus Q times V naught double prime. And then minus, differentiating this with respect to Q dot will give me MQ dot, and then differentiating that with respect to time will give me MQ double dot, and that has to be equal to 0. Okay, we can put this into standard form. So we get Q double dot plus V naught double prime over the generalized mass times Q equals 0. We recognize that we have a simple harmonic oscillator, so then this term here has to be omega squared. So we conclude that omega equals root V naught double prime over the generalized mass. So for instance, we can take a look at an example of this with the pendulum. So here we would write that the kinetic energy is 1/2 I theta dot squared. which is 1/2 ml squared theta dot squared for our BABA at the end of a string of length L. Right, so then right here, this ml squared would be my generalized mass. So potential energy, we can say is equal to mgl times 1 minus cos theta. We could drop that 1 if we wanted to. In fact, we will by doing a clever shift. So we'll just shift this one away. Actually, we won't. I take that back because cosine of 0 is 1. So that's why I had it in there. That already was the shift. All right, my apologies. So anyway, we take the second derivative and evaluate that at the equilibrium position. So we'll have an mgl. And let's see, derivative of cosine is minus the sine, so it gets rid of that minus sign. Derivative of sine is cosine. So we're just left with cosine. We evaluate at equilibrium, which is cosine of 0, which is equal to 1. So we get that our v naught double prime is mgl. So following our prescription, we have the v naught double prime goes in upstairs in the root, mgl. Our generalized mass, which is the moment of inertia, ml squared, goes in the basement. Cancel, 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 cancel. And we get root g over L, which we've seen before. So again, assuming near equilibrium and theta being small. All right, so the next two videos are going to explore the same problem, the problem of coupled harmonic oscillators. We'll be looking at 2 masses and 3 springs. And we'll first analyze it from a Newtonian perspective, and then we'll analyze it using Lagrangian mechanics.